Swayam Prabha. Digital India. Educated India.
So I hope you are able to see the whiteboard. I think last time I stopped telling you the two things. One was if I plot Coulomb criteria, which is tau is equals to sigma and tan phi. If I do that, then this is a line, straight line passes through the origin where this angle is phi. And another was shifted C plus sigma and tan phi. So this I told you this is the cohesion, this is the friction angle phi, and this was a little bit shifted, and this is C. That means a intercept is there. Now you mind that this also has the negative side because tau can be positive and negative. So this can be also like this, okay, like this one and this one. So this can be also C or minus C, whichever you consider. And so these two are the line. And I asked you, I think last time, whether a point here or here or here, which one is safe and which one is unsafe. So anything basically in between here is safe, or we call it elastic. Still the material is behaving like elastic material. So this entire zone is the elastic zone. Okay. So then we normally write it mod value of this, because this we are considering as a positive value, and so that when you plot, this negative line is also there, because here C is positive, sigma n we normally take positive. I'll show you the negative side also, and phi is also positive. So this side is basically, this is basically positive. Now this is the mathematics side of the failure criteria. That means we are saying for a given sigma n, which is the normal stress, if I know these two property of the material, I know what is the maximum shear stress it can take. So what does that mean? It means like this. It means like I am loading a sample, and if it fails like this way, if this is the failure path, then there will be a sigma n and there will be maybe a tau. So now I am limiting the value of tau. That means what is the maximum value of tau? This can be this much, and this is given by two material property. One is C, one is phi. If I know these two, and sigma n, if sigma n is known, then I can know the value of maximum value of tau, or at what value of tau the material is going to fail or have a crack like this, okay, which has an angle beta. This is what it means. All right. So this has a two material property. One we call cohesion, another is angle of internal friction. This is what I told you last time. Okay. Now I have also told you that it is very difficult to measure sigma n and tau because I actually, before the test, I do not know what will be this line. I have no idea. So what is the value of sigma n and tau? I actually do not know. I have no idea. It's just an equation where I do not know sigma n or I do not know tau. So what to do? But this is the equation given by Coulomb, and later on it has been modified by Moore. So what we do for this case? we change the axis, because that I have already told you that how to change the axis. So if this is the sigma 1, let me delete this so that you can read it properly. And if there are sigma 3, mind that this is a cylindrical sample, so sigma 3 is all around. Okay. Now the question is this sigma n and tau, whether I can rotate it in sigma n and sigma 3 plane. I will not plot it in tau sigma n plane, rather I will plot it in sigma 1 sigma 3 plane, or I rotate this stress. And this I told you before also, because if you see this is the rotation angle beta, so I can easily rotate it, right? Now this can also be done by Mohr circle. So I am plotting the Mohr circle so that you understand much better way. Now this is a now classical case of stress transformation. Okay. So I plot Mohr circle. This is sigma n axis and this is tau axis. I hope you can see that. Now since sigma 3 is the minor principal stress and sigma 1 is the major principal stress, so there will be one point here somewhere and one point there somewhere. So this is sigma 3, sigma 1. So I can draw the circle, right? I can very well draw the circle. Now mind that sigma 3 is known to us because this is applied. This is applied. Let's say before the test, we applied 5 MPa or 2 MPa, whichever the student want to apply. And for the entire test, this will be maintained, this value. Okay, this will not change. This is a constant stress will remain applied on the sample for the entire duration of the test. And now from the top, we are applying this sigma 1, and this value here, what I am showing here, this value is when the material has failed. Okay, this is when material has failed. So this point represent this, the sigma 3 0 point represent this plane. Okay. Now let's say this is the angle beta. So I draw this angle beta. Okay. So this is now angle beta. Same angle beta what I drawn here. From this x-axis. My sigma 3 is now x-axis. So I draw the beta. Now wherever it touched, I draw a tangent on that point. Okay. So far you are with me. Now, can anybody tell me what is this blue line I have drawn? What is the equation of this blue line? What will be the equation? Anybody? So this is the tangent at this point. Wherever this line has touched this.
I think it is sigma n and tau. Basically, the limited, the maximum that can be applied.
Right. That is that failure envelope what I have told you. Tau is equals to C plus sigma n tan phi. Now why I am saying this? See, this circle, this is what you have to understand. Okay. This circle, more circle I have drawn, each point represent a failure case, because this is the failure stress. So basically this sigma 1 0 at this point, it represents this plane. So it indicates that at this particular point, this is a failure. Okay. Similarly, this sigma 3 0, each point represents a failure because this is a failure circle. Now, this has failed with an angle beta with the horizontal. So when I have drawn this angle beta here, wherever it touched, now if I draw this tangent, this is what has given by the the Coulomb. And he said, whatever the sigma n and tau in this plane is the failure stresses. So tau will be the failure stress and sigma n will be the normal stress at that point. So this represents this plane, this point, where it has failed. I hope you understand that. So this is C and this angle will be phi angle. Okay. So this is that line. Now, if the beta was very high, then my tangent would have been somewhere here. Okay. So there may be a point right here where it will be parallel to this line. So phi will be 0. Phi will be 0 means there is no friction in that body. We normally do not get that. Okay. But theoretically it is possible. Okay. Normally we do not see any material which doesn't have a friction. There will be a phi angle. So there are some material which does not have cohesion. C is 0, but friction will be there. Okay. So this is that limiting case. So now I can draw very well. Here this is my sigma 1 and this is sigma 3 and this is then angle beta. Now tau is here, sigma n is here. This thing I can show like this. Basically, this is just for the representation to understand. So now, if this is the case, then sorry. This is my tau, and from here to here is my sigma n, right? Because this point is my sigma n tau point. This sigma n tau point. Okay, whatever is there. Okay, so far clear, I hope. Now, let us see what additional information we can extract from this Mohr circle. Now, let me take it a little bit this side if I can. I am extrapolating this line here. Okay, I just extrapolated. So this angle is also phi, same. Okay, now this is a tangent. Let's say this is the center here. So I use another color. Now, if I connect this, all of you know this will be 90 degree, right? Okay. This will be 90 degree with the tangent and the radius. This is from simple geometry, you know. Okay. Now, can anybody tell me what is this angle? What is the value of this angle?
90 plus 5.
Plus alpha. Phi, sorry.
It is 2 beta, right? Do you agree or not? Because this is also beta, isn't it? This is also beta. Because these two are radius. So if this is beta, this is also beta, so this is 2 beta. So I think somebody says this 2 beta will be now 90 degree plus phi. Okay. So if this is the case, then I write beta is equals to 45 degree plus phi by 2. Or in other words, phi is equals to 90 degree minus 2 beta. Means from here I can directly write. So I told you before, phi is one of the material property, the angle of internal friction. So the angle of internal friction, I may be able to calculate if I know this angle beta. That means how, at what angle this has failed. If I can estimate that after the rock has failed, if I can measure that angle, then I will be able to calculate this phi. Okay, I'll show you another way also, but this is one of the way of calculating it. Okay, so now I have to now calculate the value C. Okay, I have now calculate the value C. So phi is already known. Now how do I calculate C? If phi is known, do I know C or I don't? Okay, before I go there, let me now convert. Okay, now this was sigma n, and what is this value from here to here? Let me delete that so that I will be able to write this. From here to here, can anybody tell me what it is?
Sigma 3 plus sigma minus sigma 1 by 2.
Exactly. This is the center, right? Okay. This is this. Now, if this is the case, how much is this from here to here? This is already sigma n, or can I write what is sigma n? Sigma n equals to sigma 1 plus sigma 3 by 2 minus, if I get the radius r, so r, what should I write? Cos pi minus 2 beta, right? See, what is this angle? And this is the radius r. Okay, so this is what is sigma n. Now, what is tau? Tau is this length from here to here. From here to here is tau. So tau we will write r sine pi minus 2 beta. Okay. Now you already know what is 2 beta is 45 degree plus phi. Okay, 2 beta is 2 beta, sorry, 90 degree plus phi. So you put it there. This is pi 180 degree. So you can manipulate. And what is r? The manipulate means what I'm saying is you can replace the beta in terms of phi. Okay, here you can replace it, and r you can replace it by what? What is r? Radius is equals to sigma 1 minus sigma 3 by 2, right? This is what is r. So now sigma n and tau we can very well replace by this. You put the r here and you change beta 2 beta by 90 degree plus phi, and you manipulate and you will get the sigma n and sigma n and tau in terms of sigma 1, sigma 3 and angle phi. Okay. And if you do that, once you do that, and my equation is tau is equals to C plus sigma and tan phi. My equation is this. And now if you replace this here and this sigma and here and rearrange in terms of sigma 1 and sigma 3, the equation becomes something like this. Sigma 1 minus or equals to sigma 3 something like n plus sin phi by 1 minus sin phi plus 2c cos phi 1 minus sin phi. So I am leaving it up to you to prove it in your home. Okay. I am not proving it here. I have given you ample hint how to do that. So you have to just replace beta and r by appropriate equations and then just rearrange, and you will see this equation converts to this. Okay. This equation converts to this. Okay. Now we normally write this parameter here. This is called triaxial factor. We normally term it by n phi, which is 1 plus sin phi by 1 minus sin phi. This is normally more than 1. You can see that if phi equals to 0, it is 1. But as I told you, phi will be never 0. So for any value of phi from 0 to 90 degree, this will be more than 1. Okay. At phi equals to 30 degree, value becomes 3. So there is a n phi value, which is a triaxial factor. And if n phi is this, you can also prove 2 cos c as 2 cos phi by 1 minus, sorry, not 2, 2 is not there. This will be square root of n phi. I think you can do a trigonometric manipulation. I think you have done in your class 12 and all this. So this will become like this. So the above equation, I am writing those equation again and again so that it goes to your mind. So my equation was tau is equals to C plus sigma and tan phi. And now I have converted it. Sigma 1 equals to sigma 3 n phi plus 2c square root of n phi. Okay. Now you see, these two equations are exactly the same. There is no change at all. We have just done the, we have just transformed the axis. That's it. Now here, why we are doing like this? The reason is the sigma 1 and sigma 3 are measurable. We can measure it because sigma 3 is applied. We know how much value we have applied, whether 2 MPa or 3 MPa. And sigma 1 we are measuring at what stress it has failed. Okay. Now, if those two are known to us, then I can form the equation. Okay, means I know the completely these equations, or I can not only the equation, I will know the values also. Now, provided that C and phi is known, okay, Now from this we will be able to calculate C and pi. I will also give you a problem to solve. But now we understand the equation not from the mathematics point of view, from the rock mechanics point of view. See, I told you very beginning that in a rock type material, which is a frictional material we normally call, cohesive frictional material. So in order to break the rock, you have to overcome two things. One, I told you, the friction between the particles like sand, silt, and if clay particle is there. So you have to overcome those frictional forces which is generating while you are trying to break it. And second thing is you have to overcome the cohesion, that is the bonding or the adhesive which bounded the particles. Now you see in the equation, this is my failure stress. Okay, this is the failure stress. The stress applied normally to fail the rock. And you see this N phi is completely controlled by friction angle. The more the phi, the more is the value. Okay. And here also you see the cohesion is there with multiplication with the frictional part. So you can see this failure stress is now related to friction and cohesion, both friction and cohesion. Okay. Plus there is a confining stress. Okay. That means whatever we thought this material is composed of, and if you want to break it, that friction and cohesion, and it has now come to a mathematical form. Okay. So the physical system we were able to answer by Moore Coulomb this criteria, that to fail the stress, to fail the rock, the amount of stress is dependent on frictional angle, depends on cohesion, and depend on the confining stress. Do not forget about that. That plays a very important role. Now, if I go a little deeper into this equation, okay, it is just not an equation. That is what I am trying to tell you. See what Coulomb has given us. This side, he has said there is a cohesion and there is a friction, and there is a, this is also a confining stress, but it's a normal stress in this case. So we can say this part is my shear strength. This right hand side is my shear strength of the material. Now this shear strength depends on the cohesion and the friction angle as well as the normal stress acting on that plane. And this one we call shear stress. Okay, this we call shear stress. So when does the rock fail then? When tau is greater than the right hand side. That means the strength. Then rock fails. So when left hand side, which is tau, is more than the right hand side, that means C plus sigma and tan phi, the rock fails. So as long as strength is more than the stress, rock will not fail. Similarly, with the same concept, I can say this is my strength. So this is also the strength. And this is the failure stress. But in a normal plane. Okay, not in the shear plane, in a normal. Okay, normal or the axial stress. We are converting into the axial stress. So this is Axial meaning in that axis of the sample, we are applying the load. So this is also a strength of the same material. Okay, and this is the failure. So we are just converting the axis. So this part remains strain and left hand side remain the stress. So under this situation, what is factor of safety? It is a very important concept. What is then factor of safety? Factor of safety means that it is defined as strength by stress. So in our case, the way we have written, right hand side divided by left hand side of this equation. Okay. Now generally we want this to be more than 1. Okay, more than 1. So that strength should be higher than the stress. Or in other words, if factor of safety is more than 1, we normally say material is still behaving like a elastic. It has not failed. It didn't go to the plasticity zone. Okay. So this is what it tells us when it will be elastic and when it will be plastic. If you now remember, I think in the last class, I started with that if sigma and this is theirs, I told you I am going to talk about this point when it starts to fade. That means this point is saying whether I am this side, elastic side, or I am in plastic side. Okay. So the factor of safety is telling me that whether I'm in the elastic side or in the plastic side. So if you go by factor of safety, this side FOS is greater than 1. At this point, it is exactly 1. It is exactly 1. And in this side, FOS is less than 1. Okay. So this is what the concept of strength and stress, and from that factor of safety. Okay. So I hope you understood what this failure criteria or the yielding criteria means. So there will be a strength part and there is a stress part. Now when we write it like this, in this case sigma 1 equals to like that, then we are saying that stress is exactly equals to the strength. That means we are talking about this point. If I multiply this with some factor of safety, and if factor of safety is more than 1, then I am in the elastic side. Okay. Plastic side, we do not talk about with using this equation. But as long as factor of safety is more than 1, this we are in the elastic side. Okay. Now here there is a two material property we are using. One is cohesion and one is friction angle. Okay. Any questions so far? Before I show you another thing, and then I will ask you to solve a simple problem. So what I have shown you so far, if I now plot in this plane, sigma 1, sigma 3 plane, then this will be something like that. This line, because you can see this is still a straight line. Sigma 1, sigma 3, this is still a straight line. Okay. So this is the intercept. So this is that intercept. And the intercept is 2c square root of n phi. Okay. And if this angle is psi, then I will write tan psi is equals to n phi. Okay. This is what is Bohr-Coulomb criteria in sigma 1, sigma 3 plane. So this is sigma 1 is equals to sigma 3 n phi plus 2c square root of n phi. This is that line. Now, can anybody tell me what is this? What do we call it? 2c square root of n phi.
UCS.
Exactly. Can you tell me why?
Sigma 3 is equal to 0, uniaxial compressive strength.
Exactly right.
There is
So,
no
yeah, exactly. You are absolutely right. So, this is basically UCS. Okay. And this we normally write with sigma Ci. The sigma C is compressive strength. We normally say I means of intact rock. Okay. So, sometimes we replace this by sigma Ci. Okay. We also replace it by this. Okay. So, in other words, what is saying, the moment you try to increase this sigma 3, your strength will also increase. Okay. Your strength will also increase with the sigma 3 because the n phi effect will come. Now, whether it will go like this or like very like that, this depends on the angle phi. Okay, this depends on angle phi, but at sigma 3 equals to 0, it is the uniaxial compressive strength. Good. Now, I again extrapolate it. I take it down here. Can anybody now tell me what is this? First, tell me what is the value of this? What will be the value of this? Basically, sigma,
on under root n phi.
yeah, 2c square root of n phi, right?
Yes, sir.
Okay. Now what is this?
UTS.
Where UTS, absolutely right. This is the, I would say, we write UTS, but in the bracket you will write theoretical. Okay, it's basically theoretical value. Means coming from Bohr-Coulomb. When we test, we do not find this value. Okay, whatever we are plotting it here. I will tell you why. So this is theoretical UTS, and one can say this is also theoretical UCS. Coming from basically when you test, you will get little different value, of course, because not each material will behave same way. Now, if this is the case, and every time we do not find this value, we normally find when we test. I think you did not do all those tests, but you would have then compared. It is somewhere in between. The rock is very weak in tension. You know that rock is weak in tension. You know, you can break a chalk very easily by tensile force, and it will be very difficult to break it axially, giving a uh, compressive load. You know, you take a chalk, uh, and if you give a compressional load, I'm drawing it here. Let's say this is a chalk, and if you try to break it like this, you need much more load or the stress to break it. But if you pull it, if you pull the chalk like this, it will be very easy to break. It will break like here. Okay, there is another way you can break the chalk. If you give some kind of twisting. Okay, then means twisting. You're twisting the chalk. You can also break. This is basically pure shear condition. This one, it's very easy to break. But this is pure tension. Okay, just tensile load is given and you are breaking. It is much easy. So normally it is found that rock type material is weak in tension. It doesn't go all the way, what theory says. Actually, it breaks much before. So we call this point tension cutoff. Okay, this point is called tension cutoff. So my envelope goes like this. In sigma 1, sigma 3 plane, my envelope is this. From here, it goes like that. So under this, everything is safe. Okay, under this, everything is safe. You give any sigma 3, sigma 1 point in between that, this will be safe or elastic. And if it is outside that, this will be failed. Okay, so this is what is the complete view of Moore-Coulomb. Now, as I told you before also, this is also in the bottom. Okay, do not forget about this. So this comes here and goes like this. Okay, so it's anything in between that. It is like this. Okay, this is what we like to say. Okay, now we got two things now. Theoretical UCS, which is 2C square root of n pi. This is my uniaxial compressive strength, and you can see under this we have cohesion, we also have friction. Okay, UTS 2C, although there will be a minus, but I'm just taking the value 2C square root of n pi. I'm just taking the values. Okay, this is theoretical. Both of them I'm taking theoretical. Now I'm getting the ratio UCS divided by UTS. And this will give me the value n pi. Okay. Now, this is nothing but 1 plus sine phi by 1 minus sine phi. Let's say if I give the value 10, okay, that UCS divided by UTS of a rock is 10, this ratio. Then what is the value of phi? You can quickly calculate. If you calculate this value, the phi normally come, I think, 56 degree or so. something like that it will come. If you give 20, if this ratio is 20, can anybody quickly calculate what will be that value if it is 20? The phi value, I think some 70 or something degree, if I remember correctly, or 66, 67 degree, something like that. Okay. Whatever, if it is 20, you just calculate and tell me. Now, why I'm saying
64
this,
degree.
how much? 64.
64.79.
Okay, so let's say 65 degree. So if it is 20, if it is 20, then we are getting 65 degree. This is 54 or something, I forgot. Okay. Now, what it means is, I think if I now go, the beta, 45 degree plus 5/2. So if it is, let's say, about 56 degree, so how much is this?
72 approx. If we take phi equal to 54.
54. Okay. So 72 degree. And for the next one, if it is 65 degree, this will come 45 plus 37, 38 plus say.
77.5.
So how much it comes?
77.5.
So 78 degree, let's say. Okay. Now, what is beta? You remember this angle, right? So one is almost 72 degree, another maybe 70. So you see, more this ratio, UCS by UTS, more we are going towards 90 degree thing. Okay. And this ratio, if it is very high or very large, this happens for a brittle type material like granite, basalt, okay, or maybe the glass also. Okay, if we test, this phi value will be almost 30, 35. So UCS is almost 25 to 30 times higher in a very strong brittle material. So in that case, when we break the rock in the laboratory, we find this sample just breaks right from the middle into multiple pieces. Okay. And that kind of explains that this, because of this ratio is high, this ratio is nothing but the triaxial factor. So because the triaxial factor is high, so you can say vice versa, it will be brittle, or you can say the angle of failure will be close to 90 degree. It is going towards 90 degree. Okay. So in other words, more the brittle, more the beta angle or angle will be close to 90 degree. And if it is a more like ductile material like coal or clay, which are very soft, and there this angle is much lower. The phi will be 25 degree to 30 degree. Okay. So this kind of more Coulomb, this envelope also explains something what we see in the laboratory. It doesn't explain everything. Still, there is a lot of discrepancy happens, but kind of explains that why when we see in the lab the some sample behaves, we can explain a little bit using that. Okay, before we stop this thing, I give you a simple problem which you can solve very easily, I know. This is also there in the book. Let's say A series of triaxial tests of sandstone rock reveals the following relationship. The relationship is sigma 1 minus sigma 3, 3 sigma 3 minus 75 is 0. Okay. Now, all values are in megapascal. Now, you are supposed to tell me what is the cohesion and angle of internal friction. Just quickly tell me, it's very easy. By series of triaxial tests, a student has come up with this equation. What is the cohesion and what is the friction angle? What is C and what is phi?
Sir, C 21.65.
And phi? Phi you can find. Without finding phi, how did you calculate C?
So like the equation, so this equation was given in sigma 1 minus 3 sigma 3 minus 75. So by comparing n phi will be 3 and 75 will be 2c root n phi.
So n phi is 3. If n phi is 3, phi value will be 30 degree. From there you can find out. And once phi is 30 degree or n phi you already know. So 2c square root n phi is given 75. So it's very easy. You can find out the value of C. So that is the cohesion and angle of internal friction. So by triaxial test, we normally calculate this. Last thing before we go, I think since we are in this, I showed you here with the one test only, but normally we do not do a single test. We do multiple tests because in a rock type material, no, you never believe results with a single test. Okay, you have to repeat the test. So this is, let's say, 1 sigma 3 sigma 1. Then we vary the sigma 3 and we will find this is another sigma 3 sigma 1. Then we again vary, let's say, another sigma 3 and we find sigma 3 sigma 1. Okay. Then we try to plot a line which gives us more or less the common tangent. It's very difficult to find. So you more or less draw a common tangent. Why common tangent? Because since all of them are coming from the same sample, means same rock core, so we assume their property will be same, C and phi. So if I now find a common tangent, and that should mean that sigma 1 is equals to sigma Ci plus n phi sigma 3. This is what we assume. So when I say from the series of triaxial tests, I mean this, that they have done at least 3 or 4 triaxial tests by varying the sigma 3 and they found different sigma 1 and then they plot a common tangent. As I'm telling you, common tangent, finding a common tangent is a very difficult task. And then we plot this straight line of that common tangent, and that is the equation what is given here. Okay, this is that equation of that common tangent. Okay, this is the normal way we're doing it. We normally do not do by a single test, by multiple tests. Then it also gives us a kind of a average sense. What is the value? Okay, so I stop here today. So tomorrow I'm going to go to another failure criteria, which is called hook and round.